Alright, draft physics video. Not sure exactly what I'll get to, but just a couple of things running through my head on gravitational lensing and orbits and speed and those kind of questions. So, see how this works out. It's pretty low resolution, unfortunately. So the first thing I thought of was the LIGO thing, with the two arms. Okay. And these are 2 miles each, and you have a mirror isolated. So it's all a vacuum, and the mirror's in the vacuum. And the thing I was thinking about was, here's the laser gets emitted in here, so light travels and comes back. And what you're really measuring is the wavelength of the light, so to speak, where the tons are by my theory. And you're measuring a difference in arrival time between the two waves. So one would be slightly ahead of the other one, and like so-ish. And so you're just measuring that little tiny difference in the phase of the light. And so I've sort of made the point before that, theoretically, you wouldn't need necessarily to be exactly the same length. I mean, ideally, it would be best if they're identical lengths, because then you'll have the most amount of difference in terms of the phase difference of an incident. So if the incident happens faster than the speed of light, for the amount of distance you're off, let's say this one was a foot shorter. Well, the speed of light for a foot is a certain amount of time, and if the event has a frequency that happens faster than that 1 foot time, then you would lose it in terms of your control leg, so to speak. It would have already passed before you received it. The other one, you wouldn't get the same difference. But I mean, it would only be for events that were happening that quickly. In any slower event, you could clearly be able to pick it up, even if these arms were different lengths, as long as you adjusted your instrument ahead of time so that these two beams, by making minor adjustments to the mirror, these two beams are lined up in terms of the phases on phase. So once you have them on phase, then that would be the only, then you can measure the difference regardless of whether they're exactly the same length or not. So, going to take that a step further, I have to wonder why it matters that they're 2 miles long. Why bother with a 2-mile long tunnel for the purpose of measuring gravitational waves, which are really just supposed to be the mirror itself is being moved. And the mirror doesn't really care how far away the light source is. That's not going to change how much the mirror moves. The mirror is going to move a certain amount, and they have it suspended deliberately to isolate it from the ground. So they're isolating it from any movement in the tube itself. So the tube that's carrying the light, they're not really measuring that. And it's a vacuum, so there's no atmosphere they're measuring the movement in. So it's really just the movement of the mirror. And the mirror is going to move, how would the mirror know that, let's say you made the arm 4 miles long? How would the mirror know this was 4 miles now rather than just 2? I mean, the mirror is still going to move the exact same amount. So, and when the mirror moves, that's going to be a change in this phase. And so what I'm not understanding exactly is how does having this more space between the mirror and the emitter change how much the mirror moves. Because it's really not about creating distance between each photon. I mean, the argument isn't that space is created between each and every photon. And even if it was, it wouldn't make any difference. You couldn't add up that space to create more space. I mean, that is theoretically, I guess you, in some sense, I suppose that might be what they're arguing, is the photons, which they think are some kind of thing in a field, some sort of electromagnetic field. So the electromagnetic field is somehow going to add extra space between each one of the photons, a proton's worth of space. So I guess if you did that, you could sort of understand that if you have 1, 2, 3, 4, 5, and then you increase the amount of space, you know, between each and every one of them, that you know, then you could somehow say that it adds up, and you can, so the more photons you have in the space, the more you add up how much the mirror moves. See, again, it just really has to do with this mirror moving. No, it doesn't really have to do with the photons pushing the mirror. The photons aren't going to make the mirror go bigger. I mean, they push the mirror. So it can't have anything to do with the light. So it's just about how much the mirror moves. And you're not going to see how much more the mirror moves any better by having this 2 miles long. There's no advantage to it. How does having this tube 2 miles long make the mirror move more? That would be the question. How does the mirror know how long the tube is? How does it know that, oh, okay, if it's a 4-mile tube, I'm supposed to move more than if it's a 2-mile tube or a half-mile tube or a foot-long tube? Why should the mirror care how long the tube is, I guess is the question. I find I find the answers unsatisfactory. Again, just because the fact, like, say if this mirror was connected to the Earth, okay, then you could sort of understand that if the Earth expands, like this whole hunk of rock and everything else expands, that would move the mirror. So that you could sort of understand. The mirror might be moved because the rocks are moving, but they've isolated it from, they're deliberately trying to isolate it from the movement in the Earth. So they're trying to make the mirror the only thing that moves. And, you know, so it doesn't really make much sense to me. Doesn't make any sense, actually. Well, the whole concept is, you know, weak in my opinion, but yeah, this part just doesn't make much sense. So anyway, the other thing I was thinking about was the neutron star idea. You know, that they discovered in 1974, and they gave them the Nobel Prize in 1990. So they waited 20 years to give them Nobel Prizes, and it just seems like it might have been coherent or whatever the word is, with this whole subject of gravitational waves becoming popular and the idea of let's go find these things. So that might be a bit of a you know, the fix is in sort of thing. Like all of a sudden this was the vogue science. So anyway, so you have this pulsar, which apparently is the same thing as a neutron star. Supposedly, maybe, I don't know, not entirely, but in some way. And the idea is it's tiny, okay, let's say really small. I don't know how much smaller. So if a regular sun is this size, it's much smaller. So it'd even be smaller than that, relatively speaking. And so the whole point of this thing is that there's, I was thinking about how gravity works. And so let's say this is our sun, and let's say Mercury's here and the Earth is here and Saturn is here, and yeah, these aren't, you know, anywhere close to right, but I'm just saying you could draw a circle that would be that size, and essentially all these objects are moving the speed that would be the surface speed if the sun was that big. So if we just took the same mass of the sun and we made it as big as the Earth's orbit, then you could sort of think of the Earth just rolling along the surface of the sun. That would be that big with the same mass. And each object is sort of doing the same thing. You're just rolling on a much thinner and thinner and thinner sun. One that's, much more diluted. And so your speed is a lot slower the further you go out, because there's a lot less density between you and the center of the sun, because you've expanded the atoms of the sun by this percentage. And so essentially these things in a sense are traveling all the same speed relative to the arc of their circle. So relative to this arc, all these speeds are the same because they're orbits. So they have to be, in a sense, all the same speed, in the sense that if you pushed one of them into the other guy's orbit, they'd be traveling the same speed as that thing. But how you push them is the tricky part. You can think of forcing something, and so it doesn't work with like runners on a track. The idea doesn't work because the track runner is creating all of the he has to sacrifice his velocity to turn into the corners. So the tighter you make the corners, the more velocity he has to sacrifice actually to do the corner. So he's losing velocity to cornering. But we all have this idea that if I have a spinning ball and I can make the track that it's spinning in smaller and smaller, that it will go faster and faster. And the same idea of a string. If I have something twirling on a string and I make the string shorter, pull it, I can make the thing going faster and faster and faster. So the idea with these neutron stars is they they do the mathematics of making something very small, like the size of the Earth is the mass of the sun. So instead of having an orbit like Mercury, and you could be going 100,000, say, miles an hour, let's understand that light travels at 670 million miles an hour. So it's not a very big percentage of the speed of light. But in these neutron stars, they're almost arguing that it's going half the speed of light in their orbits. So this one they discovered, the first one they discovered, is in one of these kind of weird orbits where, see, they haven't actually found the partner neutron star because it's not emitting any radio waves, or they claim it's not pointing the right direction or some kind of bullshit. So they only see one of the objects, the one pulsar, but it's the irregularity of its pulsing. It's 7 hours it takes to go through an orbit. So let me just draw the orbit, I suppose. So the orbit is supposed to be something like this. They're highly elliptical, and the two objects just meet each other here in the close proximity, and then they swing around each other. So this one goes around this way and that one goes around that way. You can sort of see that. So it sort of looks like a figure eight, but they're not really figure eighting. So this is the key gravitational moment, is right in here, and this is when they're reaching their highest speeds. And the point is they're very small, Earth size. So at this closest distance, maybe their distance is really, really close, and they both have the mass of the sun. So it's sort of like thinking about compressing the sun. So say if you knew the speed of something orbiting the surface of the sun, what speed you had to go not to fall into the sun or not to fly off of the sun. So there's probably a speed, I don't know, 300,000 miles an hour? I don't know. I should try to figure that out or find that number. But you can see if I made that circle smaller, if I pulled the string made that arc smaller and smaller, that speed increases and increases. So that's how they get up to these really high speeds, is they got these things going really close to each other, and they're highly massive. Now, my argument would be is that these are really fragile orbits, and that anything from the outside world could come in here and hit one of these things, and this orbit is broken. It's not going to be sustainable. And then these objects are going to fly off at really high speeds. I mean, incredibly fast. Just as the thing with the string. Now, if I pull the string, and and there's a thing going around, and it's going really fast because I've pulled the string and got it in really tight, and then I break the string, it flies off at a higher speed than if I had it really big loop and then let it go. It doesn't go off very fast. So these things would, if their orbit got disrupted, and by the way, it's a declining orbit, so they're supposed to eventually start circling each other, but in 300 million years. And they claim that the thing is now producing, like, I don't know, 700,000 watts of gravity waves. They didn't detect them with anything. That's just their mathematical approximation based on, they think any orbit that deteriorates, that is where the things start crashing into each other, getting closer, like the sun. Say if the Earth was actually orbiting into the sun eventually, it's probably doing one or the other, but anyway, if it was going to go crashing into the sun, they would claim that produces gravity waves. So it's when you're changing, you're not in a consistent orbit, and your orbit is decaying, that you're somehow producing these gravity waves. But anyway, so I would say it's just speculation. I mean, just as a question, like, what's the explanation for this? If this could happen, I mean, first, these figure-8 orbits don't seem to me that you'd have enough. Once this thing orbits past here, and once this one goes past here, I don't see how the gravity is enough to stop that huge momentum, out this way and out this way, going half the speed of light, or something like it. How these masses, as they're moving away from each other, have any hope of stopping that acceleration and somehow getting it to go back towards, in the opposite direction, make a U-turn essentially. I don't. That doesn't look right to me. But anyway, I don't want to do the "it doesn't look right" argument, but it doesn't look right. So what do I want to? So I was just thinking about the idea that this orbit gets disrupted. What if this orbit gets disrupted? Then theoretically, you have this neutron star with the mass of a sun, that's the size of the Earth, hurling through the universe at maybe half the speed of light. Now, we don't have any evidence that that happens. There's nothing in any photo we've taken where, a series of photos year after year where we see some object plowing through a galaxy, just annihilating as it goes along. I mean, that's a bullet. That's a substantial. A sun with half the speed of light velocity. If you do the calculations, that's a huge momentum number, and it's going to take a lot of stuff. It's going to have to hit a lot of stuff. It's like a train hitting those little barriers, that they put where the station is, and it's supposed to stop a runaway train. Well, it's going to take a lot of those stops it has to plow into before you're going to slow that sucker down. And but the other argument I make is how they get these speeds in the first place, and but that argument's answered by the fact that they make this matter do this supermatter thing. So see, if they can make matter start to go all the way down to the size of an atom, they can create preposterous speeds. You can make something go light speed if you take the mass of the sun and you make it the size of a baseball and then have something orbiting it. Then the speed, you know, relative to that size would have to be proportionally insane. So it's like just taking the solar system that exists now and you make it half the size. Then the speeds would all have to double. And you make it a quarter the size. And then, they have to quadruple. And so the smaller you make the volume of the mass, and the shorter you make the distances between the objects, which I guess is the key point. And then it's possible to create these velocities, but I don't. There's a natural consequence, is all I'm saying, to doing that, and there's no evidence of the consequences being observed, in my opinion. But anyway, so the other argument I was going to make was the one about how, I'm kind of running out of space in my sloppy drawing, but anyway, the idea of what causes, gravity is this absorption, in my opinion, of this, exterior force. But even if you just thought of it as acceleration, that acceleration is the key component to what gravity does, is it gives something acceleration. And that would be something we could detect, because acceleration would be like an absorption. So you could sort of understand that whatever amount of velocity you're absorbing would be detectable in the field is now absent what you consumed. So if we just make it that simple without getting the specifics of my argument, maybe that's an agreeable way of understanding that the thing that changes in the universe when something's in gravity is that as it accelerates and maintains the acceleration, converts it into a velocity, converts the acceleration into a velocity, and that's essentially what the suns are doing. So as they get closer together, they're converting the motion towards each other into their forward motion in space, their orbital motion. So they're converting the gravitational acceleration, the acceleration towards, because the two things are moving, that acceleration towards ends up being acceleration in the direction of their motion. So they move faster instead of moving closer. Yeah, something like that. But it's the same problem that we have. You can't keep going. You can't keep gaining acceleration that way. You only get one little boost, and then it's like us being on Earth. We're held up. We can't fall into the Earth because the Earth won't let us. So our acceleration is negated in the sense that it doesn't convert into a velocity. So we don't have any velocity anywhere because all of the acceleration goes through us and just gets converted into the chemical energy we're pushing down on the stuff below us with. The pressure, the atomic pressure, the pressure of our atoms on pushing on the other atoms is what our acceleration is converted into. So instead of it being converted into our velocity, us moving, it's converted into us pushing. So, yeah, so that's an interesting part of this whole orbital stuff, is figuring out how you convert this attraction towards, motion in this direction into motion in this direction, orbiting. But there's still a limited amount you can derive. But like I said, the smaller they make these centers, the center is what decides how fast. So it's just like this argument before about the Earth and Saturn and Mercury. The speed is going to be dictated by how big this arc is. So if you can make the arc smaller, then you can increase the speed that you would have to maintain an orbit. Yeah. So anyway, those are just some questions I would pose to somebody who has a rational explanation or input in some kind of useful way. This interferometer is the interesting one because it was invented. The first purpose was to measure drag of the actual photons, and so for that purpose, measuring a difference in speed because distance had changed, and but that was going to happen throughout all of space because it's an ether, so the drag would be affecting the photons, not the mirror. In this case, they're claiming the mirror's doing the getting affected, and that's where this gets funky in terms of, well, why do you need the distance then? What purpose does the distance serve in deciding how much the mirror moves? Because that's all you're measuring here. They're just measuring how much the mirror moves. And so how does this extra length help when all you're looking for is a change in phase? How do you make more of a change in the phase by having the light travel a longer distance? It's not going to change the phase anymore. What's going to change the phase is how much this mirror moves. If it moves this much, then it'll move the phase this much. And that's all there is. This is totally superfluous. So if somebody can explain why this 2 miles is necessary, I'd be curious. How does the 2 miles change how much the mirror moves? Or how does a movement in the mirror why do you need 2 miles of light to detect the movement in the mirror? How does it make the change in how much the mirror moved more detectable? How is having 2 miles of laser beam, 2 miles there and 2 miles back, 4 miles of laser beam, how does that help detect how much the mirror moved? Okay. So that's enough. This resolution just isn't good enough. I'll just see if I flood it with more light, maybe. Just not enough light, I guess. But I don't know. I could probably find a little light of some kind. Yeah. Well, I'll have to work on it. Yeah. Then I'll get some other weird shadow. But anyway. It's a better scale anyway for drawing, but it's just kind of ugly. Like I should care. Anyway, so until next time, and sorry if the sync is a little bit off here. It looks off, so we'll have to see. Off. Yeah. Anyway,